In the previous lecture, I discussed the theory of electromagnetic field based on the classical equations, that is the Maxwell's equations. We identified the correct degrees of freedom and also identified a important property of gauge invariance of those equations. So, when you use the vector potential as a dynamical degree of freedom, there are unphysical components which are used for convenience in writing down the equations, but which can be eliminated later by imposing constraints. So, the summary of all this can be said that the photons are massless particles with helicity equal to plus or minus 1, and that is a language which gives the appropriate Lorentz group representation to which photons belong. The both helicities together make a theory which is symmetric under parity, and in describing the theory, we found it convenient to use the covariant language to make the Lorentz symmetry manifest, but in order to do that, we have to use the vector potential, or which is also referred to as a gauge field, A mu. This has 4 degrees of freedom, while the actual degrees of physical field are only 2, and so we saw how the imposition of gauge fixing constraint can be removed or can be used to remove the unphysical components. So, constraint of gauge fixing then remove the and that is the basis of the symmetry, which is referred to as a gauge symmetry. The directions specified by those symmetry transformations are not physical, they do not change any observable values, but they are convenient in order to write down a formulation which looks algebraically simpler. So, this was all based on the equations of motions, and we need to give a little more general framework to go to quantum theory, which goes beyond the classical equation of motion, and for that reason a different language of describing this same theory is appropriate, and that language is now the standard formulation for describing a general system of fields which are known as gauge fields, and that has a direct connection with symmetries as well as the accompanied features like conservation laws. So, this formulation starts out with constructing a local symmetry for a particular set of fields. There is no mention of what are the equations of motion at this stage, but we first construct certain operations for the fields which appear in the theory, and then worry about in which way these fields are going to evolve and what is the corresponding Hamiltonian or the Lagrangian, and then the equation of motions will come out from that particular analysis. So, the concept of local symmetry is to actually go beyond the concept of symmetries which we have seen earlier in the course, where we have essentially discussed the symmetries which can be called global symmetries. So, these global symmetries have parameters of whatever the symmetry transformation may be, and these are independent of the position or location in space time. For example, the symmetries which we have heavily discussed, this Poincare group symmetries which included translation, rotation, boosts, and even going beyond parity, time reversal, things like that. And those symmetry had parameters, for example, the rotation angle, and the angle was the same over the whole space time. It was independent of the particular location. Now, this symmetry is common in many theories. Poincare group just happens one particular example, but it can be often associated with specific choice of a basis, and one can perform a transformation of basis which changes the values of various components, but the overall observables are independent of the basis choice, and so they will be independent of those particular parameters specifying the orientation of the axis, and they all correspond to particular choice. And that is the concept of invariance, that observables do not change when you change basis. Now, local symmetries extend this concept to a next level by saying that not only there are going to be transformations, but the transformations can be dependent on the location of the particular point. So, in local symmetries, So, this extra freedom of choosing arbitrary transformation at different points certainly enhances the degrees of freedom of the theory, and we have to find a interpretation of what this extra degrees of freedom do, and also ask whether such extra degree of freedom have any physical meaning in the problem which we are dealing with, and if that is so, then we have a new framework to study an extended theory. So, the and it turns out that taking a global symmetry and constructing this local symmetry out of it by changing these parameters as a function of space time location produces a theory which is a gauge theory, and we will now see explicit construction of it in a specific case of the quantum mechanics which we are dealing with. Now, historically this concept of space time dependent transformation was introduced by Weyl in the context of Einstein's general theory of relativity, and many of the terminology for that reason which has entered this concept of local symmetry comes from the phrases defined and used in general theory of relativity. So, Einstein constructed the general theory of relativity based on the principles of equivalence and constancy of speed of light, and Weyl then asked whether one can go beyond this general theory of relativity in a certain manner. In particular, the postulates of general theory of relativity were such that it left the space time invariant interval, proper time or proper distance unchanged when one performs arbitrary transformations. So, the question was that ds square can also be written as minus d tau square is an invariant The question of Weyl was that this is an object with dimension of length, and what if the standard measuring rod which is used to specify the length had different size, at different points in space time. And that is the reason for the nomenclature gauge theory or gauge degree of freedom. Gauge literally refers to a measuring rod, and this extension turned out to be meaningless as far as general theory of relativity was concerned, because Einstein quickly pointed out that such a arbitrariness in measuring rod is inconsistent with the principles of general relativity. The postulates of equivalence and constancy of speed of light do not allow such a degree of freedom, and so the concept had to be put aside, but the name, the gauge degree of freedom, got stuck, and it was resurrected when the concept of local symmetry came back in quantum mechanics. So, that is a little bit of history of how the name gauge theory came about, and the concept was resurrected when quantum mechanics came along. So, and here indeed there was a object which was unobservable, and that is the overall phase of the wave function. One can measure relative phases between two different wave functions by doing an interference experiment, but the common phase was unobservable, and so it was a phase symmetry which can be called a global symmetry. And then Weil's idea was to convert this global phase symmetry to a local phase symmetry and see what happens to the theory, what are the extra components which appear, and that is what I am going to construct explicitly, but we do not call this whole structure local phase theory, we still call it a local gauge theory, and that has to do with the way history gives names to various ideas as things develop and get revised. So, let us give some basic definitions that we want to construct a description where the phases can change from one point to another, but the overall theory does not see this particular change in the phase. So, the basic object is a wave function for a particle, let us call it electron or any other charged particle will do, and let the transformation which we want to implement as this local phase transformation be specified with the object we will need this particle to be charged, because as we have seen earlier in the discussion of Klein-Gordon equation as well as Majorana fermions, that the wave functions become real if we have neutral particles. So, to get the phase we need a charged object, and the various constant inside here are stuck up with a little bit of foresight, so that the equations turn out to have the same form as we have used them before, and they are all the fundamental constants of charge, speed of light and Planck's constant, and lambda x is actually the real object which varies from one location to another. So, we want to develop a set of equations and Hamiltonians etc. for this particular object. So, that will have derivatives, both space and time derivatives of psi also appearing in the equations, and we would want a prescription which does not depend on this value of lambda, and to do that the derivatives also need to appear in such a way that they transform the same way as the wave function does. So, then the whole thing can be just factorized out as a overall proportionality constant, and then the theory does not care about what that proportionality constant is, because the equation of motion the right hand side will be 0 and you can multiply by any non-zero constant and it will have the same solutions. So, the derivatives should also transform the same way to keep the equations independent of this phase which is parameterized by this function lambda x. Now, clearly an ordinary derivative does not do the same job, because if you try transforming according to this particular rule, you will see that there is a derivative d mu which can act on lambda as well, which will produce an extra term. So, d mu psi x will not be the same phase factor times d mu psi x. So, we have to define a new kind of derivative, and the name for it is covariant derivative. And this is rather easy to see, but I will write down the operator, and it is easier to see the consequences of it. That we will define the covariant derivative as an ordinary derivative plus I e by h cross c times a mu, where a mu is a new object. We have stuck it in the theory at this particular stage by hand, and then we will have the property that a mu will be a function of space time as well, that so this is the transformation property we needed. Now, we can stick in the various quantity of what is going to happen to this covariant derivative, and we will see immediately that if you take psi to this particular object e raised to I, then d mu will operate on it. So, there will be one term which d mu operates on psi, but there will be a partial derivative of mu which operates on lambda, and so this overall factor will come, but there will be an extra term in lambda, and that term needs to be cancelled, and that can be achieved by changing this extra quantity which we have inserted also changes, and that change is exactly the one which we have seen before, and that was the reason for using all this constant in a particular way, that the derivative will produce d mu lambda and then a mu will also change by minus d mu lambda. The total result is that the whole object transforms by the overall phase. So, once this overall phase is outside, then one can now construct any complicated equations or Hamiltonians out of the wave function as well as this covariant derivatives, and the whole theory is invariant under this local phase symmetry, but we have explicitly added the extra degrees of freedom. There was a phase, but now we have to add an extra gauge field a mu, which also gets connected to the transformation in the phase. So, this is a whole structure of the theory. The new degrees of freedom is explicitly appearing in the theory, which is this gauge field a mu, and we can now explore what all features come out of it. So, this structure actually described in a geometrical language which is called differential geometry. The phase is called a fiber bundle, and the group which specifies this phase is the group corresponding to rotation on a circle. It is just a angle which goes from 0 to 2 pi, and it is periodic. So, this is actually a much more formal and mathematically rigorous machinery. I am not going to use it per se, but these names again are commonly used. I would like to mention these particular words which often appear in many textbooks in describing gauge theories. Let me just go ahead with the definitions which I have constructed. Now, it turns out that this covariant derivative describes translations just like an ordinary derivative does, but in undergoing these translations something simultaneously happens to the phase. The phase is changing as we go from one place to another, and the label for that is parallel transport. And so, it is tantamount to carrying around a particular arrow pointing in the direction of the phase, and then as you move along see what happens to that particular arrow as you go around a trajectory. And some non-trivial features enter when this function lambda is not 0. Okay. And those are the features which now can be constructed out of this covariant derivative, because it has all the information about how the phase is changing in going from one place to another, and this feature can be again summarized in a simple way. The do not commute with each other. In particular, one can explicitly work out this commutator and that is I E by H cross C because the derivatives can produce non-trivial effects on the A, and which we know to be the definition of the electromagnetic field tensor. So, the field arises as a non-trivial commutator of covariant derivatives, and in the language of general relativity, these non-commuting derivatives actually specify the curvature of the space, and so the field in some sense measures the curvature in this space of gauge degrees of freedom. And so, we have a non-zero electromagnetic field, which means that the corresponding structure in this sense of fiber bundle has a certain curvature, and that produces a non-trivial effect on the trajectories, which will now get modified. They will not be the same as what happens in a flat space. So, this is the way f mu nu naturally appears in this whole description, and now one can go ahead and construct whatever one wants, and in particular f mu nu again turns out to be gauge invariant, in the sense that the same transformation which psi so the whole theory is gauge invariant theory can be constructed from suitable combinations of psi, d mu psi and f mu nu. And this structure is exactly what appears in the theory of electrodynamics. But we have arrived now here in a much more geometric fashion about what all things go on as one changes location and then change the phase of the particular wave function, and here the wave function change of phase ends up getting related to the strength of the electromagnetic field. There is other features which can also be seen, which play an important role in looking at the gauge invariant objects which can be constructed, and there are many such instances. I just want to point out a important case, and that is, let us define a short form for this space time dependent phase psi changes to then one can construct an object which is called a link between 2 points u x 1 and x 2, and it is defined as exponential of minus I e h cross by c integral of a mu x dx mu integrated from x 1 to x 2. And now one can see what happens one performs the gauge transformation. A mu changes to a mu minus d mu lambda, and so d mu lambda can be exactly integrated along this curve from x 1 to x 2, and it just produces the boundary term, which is value of lambda at x 2 minus value of lambda at x 1, and that can be rewritten back in terms of v of x. So, then we only have an overall constant. So, it can be written as v x 2 u x 1 x 2 and then v inverse of x 1. And this is a very useful form, because it can be maintained quite easily while multiplying such segments together. Whenever you take one segment and multiply by another, the factors of v at either end will cancel out in combining v and v inverse, and the whole segments then transform. So, this is a covariant so we have a specific object, single point object psi transforming at v times psi, and now we have a link connecting 2 points which transforms at u going to v times u times v inverse, and we can now multiply these objects of links together with psi and construct non-trivial products, and so that the whole object can remain the same covariant transformation property, and which can ultimately be factored out to do various calculations and form equations. So, this transformation shows that one can have psi bar x 2 u x 1 to x 2 psi x 1 is gauge invariant. This is a useful object, it is an extended object, it is a link. There is another form which is also gauge invariant, and this is a trace of the same link, but now taken around a non-trivial loop in the space, but we come back to the same starting point, and so we have a V and V inverse, but both belonging to the same point, and I have written this trace as a kind of generalization of this particular analysis, which is not necessary in case of electrodynamics, but can be useful in other kind of gauge theory. So, when you have a trace of V u V inverse, the cyclic trace basically annihilates V and V inverse at either end, and you have the same object returning as trace of u, and so it is a gauge invariant object as well, and this particular object is rather heavily used in analysis of quantum field theory. It is called a Wilson loop. In particular, Wilson used this object heavily in studying non-perturbative formulation of gauge field theories. So, this is also a useful feature of how we construct gauge invariant objects out of these various species, but this geometric language and how things transform is extremely useful in this whole context. One another things one can notice in this structure of the Wilson loop, one can use an infinitesimal Wilson loop as a definition of the field strength itself, because this is a cyclic integral, one can easily apply Stokes theorem to it. So, then it becomes an integral of f mu nu over the area. The area can be made infinitesimal. So, the integral will be just exponent of f mu nu times the little area, f mu nu roughly constant over the infinitesimal area, and from that one can deduce whether there is a non-trivial electromagnetic field in that particular region or not. And this is a kind of gauge invariant definition of what this field is, and one does not have to refer to any particular strength. This is actually what can be referred to as non-perturbative definition. We do not assume anything about how large or small the magnitude of the gauge field is. And so, these are useful concepts which come out from this description of the local symmetry as a gauge theory concept. There are some other things which are also useful to see, that in this description the a mu becomes a fundamental variable, f mu is constructed as a subsidiary object, or equivalently the covariant derivative is a powerful element and everything comes out from that derivative. So, the covariant derivative is actually gives what is known as the minimal coupling. Of the gauge theory. We have used it rather empirically earlier, where p mu was just substituted by p mu minus E times a mu, but looking at it from this framework of covariant derivative, we know exactly where it comes from. It is a consequence of the particular phase symmetry structure and its corresponding fiber bundle. So, that is one concept, and it can happen that this gauge field is non-zero, but the field strength is 0. This is not surprising, because f is a curl of a mu, and just means that we have a curl free gauge transformation and a corresponding gauge field. And in this case, there is a question psi x directly couples to a mu through the covariant derivative, and if a mu is non-zero, there can be situations where behavior of psi actually changes even though f mu is 0, and this peculiarity is famous Aharonov Bohm effect, where one has a setup where the electromagnetic field F mu is 0, but A mu is not, and in this region the charged particle passes through and it ends up changing its phase, which can be detected by interference experiment on the other side of the region. So, one can have a situation which essentially I am giving a crude diagrammatic representation that one sends in a beam of particle which splits and then rejoins to produce a interference effect on the screen or observable on the other side, but the paths can be such that at nowhere in the regions of path there is a non-trivial F mu nu, but one can cook up a situation such that the phases corresponding to the two paths are different. That can happen because the Wilson loop, which corresponds to this whole loop of trajectory, can have a non-trivial value, and we have seen that because of Stokes theorem, it means that F mu nu has to be 0 at some point in the trajectory, but in the center of the loop where the particle does not go through, it can be non-zero, and then the Wilson loop can have a non-trivial value, and so one has an interference effect with a certain phase change. So, one can have a situation of two different setups. In one case, there is a electromagnetic field inside the loop, and another case there is not, and comparison shows whether the introduction of the electromagnetic field in the loop changes the interference pattern or not, in particular shifts it in one direction or the other. If that does happen, then certainly the electromagnetic field produce a non-trivial effect, and that can be paraphrased as flux is enclosed inside the loop, and so one can observe this peculiar feature and the various concepts which we have introduced in this rather non-trivial experiment, and it is certainly experimentally observed, and in that particular sense, in a sense A mu is more fundamental than F mu nu, because one sees the effect of A mu directly on the wave function even when F mu nu is absent. So, these are all the useful geometric concepts connected with gauge field and its symmetry properties, and now we will go on to the next stage, trying to couple it with electromagnetic interactions of Dirac particles.